For this video series, we've partnered up with MegaRide to discuss the most important parameter of the car's performance, the tires. In our second episode, we'll discuss tire temperature, how it completely defines the behavior of the tire and what you can do to optimize it. Hello everyone, this is Bruno. We're glad to be partnering with MegaRide to give you advanced content on tire performance. MegaRide contributes not only with a lot of the material that you see here, but we can also use their tire models to quantify many different factors affecting tire temperature. If you're curious to know more about their tire models, go ahead and check the link in the video description. If your car is off the pace for a second or more than that, and you still have good drivers, the issue that you're probably facing is related to tire temperature. This is the most important parameter related to tire performance, and it will dictate completely the grip levels and also car behavior, as we'll study together. We'll look at this problem from two different angles. The first one is thermal response, which is basically how the temperature influences the tire behavior. Then we'll analyze temperature generation, which is how temperature is generated in the tire and how it evolves throughout the stint. Alright, so what exact behavior tire temperature is influencing on the tires? The first one is tire grip, then we have the structural stiffness of the tire, and also it will affect wear and degradation. Alright, so let's start understanding how the temperature of the tire will influence grip. For that, we'll start by looking at this plot from Optimum Tire 2, our tire data and model analysis software. Here we can see a typical curve of lateral force versus slip angle. Well, it's important that we understand that we have different regions of this corner. So as you increase the slip angle, you increase the force until you get to peak behavior. The first region, the linear region, is the cornering stiffness region, as we'll discuss. And then we have the peak grip region, and temperature will affect each of these differently. If we start with the peak grip region, we can look at a plot of friction coefficient on the y-axis versus temperature. We can clearly see that the tire compound will have an ideal temperature that maximizes tire grip. One of the most important tasks of an engineer and of the driver is to make sure that the tire is as close as you can to the ideal grip. Besides that, we can also observe that there is a given temperature window, typically 10 degrees C, for a race tire, where you could consider that your tire is in the ideal window and you can consider that you have pretty much 100% of the grip. You see that the slope is really minor in this region. As you go further away from the ideal temperature, you see that the slope of the curve is increasing, meaning that for every degree of temperature that you are outside the window, you are losing more and more tire grip. It's important to notice that this plot is valid for each tire of the car, so you need to be thinking about all of them. So let's look at the front axle versus the rear axle. How is tire temperature influencing vehicle balance based on this plot? So let's look at two different situations. The first one would be the out lap or the first lap, or a cold track. So we have cold conditions or you are in the beginning of the stint. A typical race car will be rear wheel drive, meaning that it will put a lot of energy on the rear tires. Let's say that in this condition, the rear axle is at ideal temperature, while the front axle is still cold. We didn't have the chance to put enough energy on it yet. So let's say that the rear will be at its peak temperature and generate a lot of force, while the front will be too cold and not generate as much force as it could. Therefore, in this situation, we could see an understeering car. Now, if we go to the end of the stint or to a really hot track, maybe on the rear you have already way too much energy, while on the front, now you are at ideal peak temperature. In this case, on the rear, you would again lose grip because you're past the ideal window. You're not gonna generate a lot of force, while on the front, you are now at peak grip, generating a lot more force. You can see that now it's the opposite situation. We have an oversteering car. This example helps you understand how different temperature between front and rear axle will influence car balance throughout the stint or in different conditions. So far we've been looking at peak grip, but there is also the cornering stiffness region in the beginning of the lateral force versus slip angle curve that determines how much car response or stability you have. In this case, we can see that as we increase the temperature on the x-axis, the cornering stiffness is typically decreasing. This happens because the tire structure is warmer and therefore softer. So to the first steering input, it deforms a little bit more, reducing how much force it generates. This will influence car response, how much response you get to the initial steering, but also how much stability you have, because it depends on how quickly the rear can react. Speaking of structural stiffness, the tire temperature will influence, for example, the vertical stiffness, which is how much tire deflection you get for the same vertical load, in a way that, as I mentioned, as you increase the temperature on the x-axis, the vertical stiffness is decreasing. The material gets softer, and there you have higher deflection. The same is valid for lateral stiffness, longitudinal stiffness, and even torsional stiffness, which is also influencing the cornering stiffness that we mentioned. The tire temperature will also influence the wear rate that you have. We saw that we have a typical grip versus temperature curve, and now we can come up with a wear rate versus temperature curve. You can see that there is an ideal temperature that minimizes how much wear you get for the same sliding energy or energy input in the tire. This temperature is typically not too far off from the temperature of peak grip. We can also see that if you're running really high temperatures, you amplify how much wear you get to the point that you start getting graining, as you can see here. And if you're running really low temperatures, you also increase the amount of graining. If you remember from the previous episode, the rubber, when it's too cold, it will behave like glass and be more brittle. Therefore, you start losing a lot of compound with cold graining. Besides physical wear, we also have thermal degradation happening. When you keep the tires at a certain temperature over a period of time, it will change the behavior and viscoelastic properties of the rubber. Typically, you will be decreasing the grip, and this is called thermal degradation. However, for the same period of time, if you're at a higher temperature, this thermal degradation will happen even faster. So when you are overheating your tires, not only you lose grip from the previous plot of peak grip versus temperature that we saw, but you also suffer from thermal degradation and you lose even more grip. We'll discuss a lot more about tire wear and thermal degradation in our next episode. Alright, so we just learned how the temperature is influencing the tire behavior. And my next question is, how are tire models dealing with the temperature parameter? Let's analyze this by looking at a grip versus a slip angle plot. Here we can see that the data points are really spread out, and the model is not able to capture this effect. This indicates that there is one more variable, in this case temperature, that we are not taking into account with regular tire models. If we use advanced tire models, in this example Thermal Ride from MegaRide, we are able to calculate tire temperature. So now we can see that the data points are colored by temperature, and we can clearly see that the temperature is influencing the cornering stiffness and also peak grip. So now that we have a way to calculate tire temperatures, we also need a way to make these temperatures influence the tire behavior that you are seeing. For that, in this example, we are using AddyRide. You can see that now for different temperatures, we have different cornering stiffness and also different peak grip. So by using advanced tire models, we're able to take temperature into account in the tire response analysis. So what are the advantages of using an advanced tire model compared to a regular tire model? With regular tire models, if we look at a curve of steering angle versus lateral acceleration, for an overheating situation in red and another situation at ideal temperature, the model would give you the same result. So if your tire is overheating or not, you're gonna get the same results, meaning that you cannot do any temperature analysis. By using advanced tire models such as AddyRide and ThermalRide, we are able to quantify the difference between different temperatures. And for the same plot, if we give boundary conditions that are warmer and the tire is overheating, we'll see this decrease in lateral acceleration, while when we are at the ideal operating window of the tire, we can see higher grip. Since we can now take temperature into account, we can perform advanced simulation analysis, trying to, for example, prepare a qualifying lap or understand how to manage temperature over the race. I'll show you some really interesting case studies later on in the video. Now that we're done understanding how tire temperature influences tire behavior, next we need to understand how temperature is generated in the tire exactly. We'll start with the heat sources. So where is the energy coming from? The first and most important one is the sliding energy. This is the energy that you get as you slide and generate forces. As we saw in the previous episode, materials that have hysteresis will dissipate energy. Therefore, all the layers of the tire, being it compound, the rubber, or structural components, as they deflect while the tire is rolling or cornering or compressing vertically, they will dissipate energy and increase the tire temperature. Lastly, we also have energy coming from the brakes. that will be transferred to the rims, to the internal air, and then to the tire itself. Besides the sources of heat, we also have heat transfer. So all this energy is being transferred between different layers of the tire. For example, we have convection with the outside air. So the outside air is cooling down the tire, and this is the most important factor when cooling down the tires. We have convection with the inside air, increasing the air temperature and also the pressure. We have conduction between the different layers. So even though, for example, the sliding energy is coming through the surface of the tire, it will be conducting through the different layers all the way to the carcass or inner liner. And the opposite is the same. If the carcass is getting more temperature from the brakes, for example, it will also make the surface warmer. We have conduction with the road. So typically the tire is losing temperature to the road. And we will also have conduction and convection with the rim, being the sidewalls touching the rim or the rim in contact with the inside air. Now it became clear where the heat is coming from and also how this heat is transferred between the different layers. Speaking of layers, it is important to understand that the temperature of each of the layers will affect tire performance differently. As we discussed, the peak grip will be influenced by the temperature closer to the surface, while the cornering stiffness will be influenced mostly by the temperature of the carcass. So how can we measure and know the temperature of each of the different layers? So for example here, in red we have the surface temperature, which is oscillating very quickly since you have a lot of sliding energy on it. We could be measuring it with infrared sensors outside of the tire. The carcass temperature, on the other hand, is changing a lot more slowly. This can also be measured with temperature sensors installed inside the tire mounted on the rim. This can be very useful for structure analysis of the tires and also for cornering stiffness analysis. Now, how can we measure the temperature in the different internal layers of the tire? What would get us the closest to doing that is to measure the tire temperature with a temperature probe at the end of the run. Then we would get the tread core temperature. In this case, however, only seeing the value at the end of the lap, and we can see that it could be pretty different from what we're seeing around the track. And why is this layer so important? Well, because the peak grip is not only defined by the very surface temperature, but the temperature of the layers just below the surface will also be heavily connected to tire grip. Since we cannot measure these different layers, we could use thermal models for that. Here we show you an example of thermal ride. We can see the correlation between acquired data and the calculation from the model for the surface temperature. We can do the same for the inner liner or carcass temperature measurement versus model. Now that we have this tire characterized and validated for this thermal model, we can estimate the tread core temperature and tread base temperature. The tread core will be connected with the peak grip, while the tread base will be more connected to the cornering stiffness, for example. Besides that, thermal models are a very useful way for us to understand where the energy is coming from and how this energy is being dissipated. So we can see, for example, in red, this is the energy input from sliding energy laterally, and we can see it's the biggest contributor of tire temperature. Besides that, we have the friction energy longitudinal in yellow, and we can see that it's a lot less influential. We also have the losses from hysteresis in green, and so on. Besides that, we can see that the most important parameter when dissipating the energy, now on the negative side of this plot, is, for example, the external convection with the external air, followed by the conduction with the road, and then the internal air convection. Okay, so we discussed how temperature influences the tire behavior, how the temperature is generated, and now we'll do together an analysis of tire temperature data. It is very useful that we understand each of the mechanisms that generate tire temperature, because we can also understand that when we are at the track, if we change any parameter that will influence one of these, we'll be influencing the tire temperature. For example, if we have the car really understeery, it will slide a lot of the front axle, and then we're going to have a lot of sliding energy on the front axle, putting a lot of temperature, for example. If we decrease the pressure, we'll have a lot more tire deflection as the tire is rolling or cornering, which will also increase tire temperature, at least from this perspective of hysteresis and energy loss. On the other hand, a higher tire pressure would decrease the contact patch, concentrating a little more the temperature in that region. If we put toe in or toe out, it will put sliding energy even on the straight lines. And we could also speak about camber changes. The camber is not only changing the amount of energy you put in the tire, but mostly the distribution between inside shoulder and outside shoulder. When we're cornering, the camber is changing and the temperature distribution is changing. So in this case, we can see that as we corner, we are leaning on the outside shoulder for the outside tire and on the inside shoulder for the inside tire. This will influence the temperature distribution that you have. So again, for the outside tire, we are going to be putting a lot more energy on the outside shoulder and the opposite for the inside tire. When you are braking, on the other hand, on the front axle, due to camber variation, you're going to be putting a lot more temperature on the inside shoulder for both of the tires. When we are analyzing tire data, we can see this temperature distribution dynamics going on. In order to visualize everything that we discussed in this section of temperature generation, let's look at tire temperature data and analyze it together. For that, Easy Racing kindly provided us with a video where we can see the temperature dynamics. For this analysis, we'll be looking at a few laps around the VIR track in the United States, and it contains data both from carcass temperature sensors manufactured by Easy Racing, as well as their surface temperature sensors. If you're curious to know more about their YouTube channel and products, you can check the links in the video description. In this video, we'll see multiple laps connected. So the first section will be the out lap, the second section will be 2 laps later, and so on. So we can quickly see the evolution of tire temperature. So up here, we can see the surface temperature for each of the tires, as well as the carcass temperature. Besides that, we have the pressure and accelerations. So we can see, as we mentioned, that for rear-wheel drive cars, the rear will get temperature more quickly than the front because you have traction, so you are putting energy. The driver needs to be careful in the first few laps because, as you can see, the tire is still a little cold. And if you're pushing too hard, it's gonna get graining, cold graining, because the material is more brittle, as we saw in the first episode. Now we start seeing more temperature on the front and on the rear, even though the carcass temperature is still pretty low. If you remember, the biggest source of energy is the sliding energy that is on the surface of the tire. So it takes some time for this sliding energy to be transferred from the surface to the carcass. Now on lap 2, we already have the carcass more up to temperature. The carcass is around 70 degrees according to this legend over here. We can see that as the car corners, the outside tire will get more temperature on the outside shoulder, for example here in this case, while the inside tire will get more temperature on the inside shoulder. Under braking, we should get a lot of temperature for the inside tire, and in traction, we can see that we might have the rear even overheating, because we have both lateral sliding, but also longitudinal sliding. So now on lap 7, we have the carcass being very, very warm. Since it's warm, we cannot cool down the surface as much anymore because we cannot transfer the heat from the surface to the carcass. Besides that, even though on the first few laps we could be getting understeer since the front was cold and the rear was up to temperature, now we could have the rear overheating while the front is at ideal temperature. This could make the car oversteer. This is exactly what we saw in the beginning of the episode, comparing first and last lap or cold versus hot conditions. Now that we have the carcass warmer, the inside air of the tire will also be warm, and that's why we have such higher pressures compared to before. This video is very useful for us to visualize each of these heat sources and also how the heat is being transferred between different layers. It also helps us understand the effect of different setups, camber dynamics, but also how the driver inputs will influence the surface and carcass temperature. If you'd like to see many other videos like this one analyzing tire temperature and brake temperatures, go ahead and check the Easy Racing YouTube channel. You can find a link for that in the video description. Using real data, we can do many different analyses. For example, creating KPIs of average temperature, temperature distribution, or temperature while cornering. Besides that, we could use real measurements to validate thermal models. And now we can look at a few examples of what we could do with these advanced tire models. I will open results of simulations using MegaRide models in my computer so that we can perform this analysis together. So this is the plot that we've been analyzing of friction versus temperature. Here it's an internal temperature mostly connected to this parameter. We can clearly see how the temperature is influencing peak grip, and we can also define the 10-degree temperature window that we discussed. This is the temperature window that we want to be at. We can now take real data and perform a track replay. Basically, we are reproducing what the car did at the track, but now we implemented the thermal models on top of it. Now we are able to estimate the temperature in different layers that we didn't have previously. Here we can see the results. We can see how this temperature for the grip model in red is progressing over 2 laps. So we have the out lap between 0 and 120 seconds, and then we have our push lap for the second part of the plot. We define the same temperature window in green as we saw in the previous plot, and we can see how close we were to ideal temperature around that qualifying lap. Here we can see that for the front axle, we were most of the time inside the temperature window, which is ideal for both front left and front right, while on the rear, in some parts of the track, we were at ideal temperature, while other parts of the track, we were overheating. This is pretty common. Sometimes you will be overheating at a specific sector and not throughout the whole lap. So it's a balance of what sector we want to be overheating or below ideal temperature. Besides that, we can analyze how much temperature we will building through our out lap before starting our push lap. Let's say that all of our tires were actually overheating during the push lap in this qualifying session. We could then change for the next time our out lap to generate less temperature and have a better push lap. This type of thermal models allows us to do that. Not only analyzing what happened, we can do analysis to prepare for a race weekend. So we can prepare our qualifying run in order to maximize tire grip for our push laps. This is what our next case study is about. In the second case study, we connected the MegaRide models, Thermal Ride and Eddy Ride to a driver in the loop simulator. Now, ahead of the race event, we can work with the driver to prepare our qualifying session. So here we were analyzing 2 scenarios. We are analyzing a hot condition where the air and track temperature is higher, and also cold conditions where the air and track temperatures were lower. In this plot of temperature over time, we can see out lap, prep lap, and then push laps 1, followed by a cool down lap and push lap number 2. We define the same temperature window for ideal grip, and we're working with the driver to make sure that he's able to keep the tires in the ideal temperature window for both push laps. In cold conditions, as we expect, we need to warm up a lot more the tires in this preparation phase. For that, we can see in the speed trace that the driver is carrying more speed in orange for the cold condition, and on the steering trace, we can see that the driver is weaving with the steering wheel a lot more to put more energy into the tires. We can then analyze with the driver the results. We see that in push lap number 1, he was inside the ideal temperature window pretty much the whole duration of the lap, at least on the front axle, while for the second push lap, he was overheating a little bit. So we can do a second iteration with the driver where he's even slower on the cooldown lap to optimize his second push lap. Another option would be for us to run offline simulations to develop these preparation and cooldown laps. So these are concrete examples of how you can use thermal models to improve the tire performance at the track. So in this video, first we understood how tire temperature is influencing tire behavior. After that, we learned about all the different mechanisms for generating tire temperature. We saw how to apply that and analyze real measurements of tire temperature, and then how you can use simulation and advanced tire models to improve the tire performance at the track. We very much appreciate the contribution of MegaRide to this series that made it possible for us to show you a lot of the content that's here. If you're interested to know more about their work and their models, you can find a link to their website in the video description. If you would like to learn more about tire performance, you would love our seminars. We have a seminar fully dedicated to applied vehicle dynamics, where you understand the influence of each car system on tire performance. Besides that, we have our performance engineering seminar, where we're focused on analyzing real data to make sure you maximize the use of the tires by your driver and by your setup. Besides that, OptimumG offers the following services: performance engineering, where you could have one of our engineers at the track with you; vehicle dynamics consulting, where we'll help you with all your vehicle and tire development needs. Besides that, we offer simulation software, where you could find, for example, Optimum Tire 2, the ideal software for your tire data, model, and testing needs. Thank you for watching this video. If you have any questions, leave them in the comment section so that we can get back to you, and I'll see you in the next episode.